So we're going to start our discussion today with an overview of the so-called common fork join pool. And I'll describe how the common fork join pool is designed to help maximize processor core utilization in Java. So what is the common fork join pool? Well, it's basically a statically accessible pool that's available and is appropriate for most programs that want to use parallel processing with the fork join pool. And there's only one of these things. That's what makes it the common fork join pool. There's only a single fork join pool that's shared by all the different elements in a program that are trying to use the fork join pool, the one and only fork join pool. Essentially, if you don't create your own custom pool, then you will typically use the common fork join pool to run tasks. And sometimes this is explicit because you'll say, fork join pool.common pool, and then you'll make the appropriate call to execute or invoke or submit your tasks. Or, as often is the case when you start using more advanced modern Java parallel processing frameworks like parallel streams or completable future, this will be the pool that'll be used kind of implicitly when you use parallel streams. So why do we have a common fork join pool? Well, the main reason here is to optimize resource utilization by making it possible for one pool to be aware of all the cores and all the tasks and so on that are being used globally within a process. So this allows the Java fork join pool framework to have global knowledge of what's happening. And of course, as you recall from our previous discussion of work stealing, this will allow better global utilization of the processor cores because we'll have all the different tasks running in a single common pool, and therefore work stealing will be most effective because all the tasks will be there, and then the threads can be aware of all the different things that they have to run. This type of global versus local resource management trade-off model is very common in a whole bunch of domains, in the computing domain and other environments as well. Just as a simple example, in Java, there's a single global heap. And the idea behind that is that way all the memory can be managed and accounted for in one place. And you don't have to worry about having a private stash of variables or private stash of memory objects and so on that would then not be accessible to all the different parts of the program that want to allocate the memory. If you're trying to do sort of private stashes, you can end up with suboptimal resource allocation. As I mentioned before, the common fork join pool is also used by the Java parallel streams framework, which sadly we won't have time to talk about much in this class, but it's very cool. I think I'm going to give you one example of the Java parallel streams framework when we start talking about using programming techniques for the fork join pool. And it's kind of the last thing we'll look at just as a comparison and a contrast with how things work with fork join pool versus parallel streams. It's pretty cool. By default, the number of threads that are in the common fork join pool is one less thread than the total number of cores available to the underlying processing engine. And you can see here, just as an example, if we have a quad core processor with non-virtual cores or just have regular good old cores that are not hyper-threaded, then in that case, the size of the common pool will be the number of cores minus one. And you'll see in a second why the minus one is important. So if you were to run your program on a quad core processor and you were to print out the common pool parallelism accessor method, get common pool parallelism, if you were to print that value out, then you would get 3. So it's one less than the number of cores. And the reason for this is that the thread that's used to invoke the processing of the fork join pool, common pool, will also be essentially used to perform parallel computations. So the calling thread, which could be the user interface thread or the main thread or just whatever thread is the one that kind of starts the wheels in motion, that will also be included in the pool along with the other threads that are part of the common fork join pool. So that way you will end up leveraging all the processor cores. It's just that the calling thread is going to pitch in and help out. Much like we talked about earlier when we discussed the semantics of fork join task join where it'll pitch in to do the processing. Now, this default number of threads is pretty effective most of the time, but there are certain situations where the default number of threads could very well be inadequate. And this problem commonly occurs when you're using the fork join pool or the common fork join pool for blocking operations. For example, you might be downloading a whole bunch of images from web servers, and there may be more images you're trying to download at any given point than there are cores available to download them. And in this particular situation, as you may recall from our other discussions about thread pools, when you have I/O bound computations, you typically need to have more threads. Otherwise, you'll either underutilize the processor cores because you'll have all the threads, the n threads, where n is the number of cores, but that's less than m, the number of images you're trying to download. You'll have them all blocked, but in fact, there could be more processing done if there were only more threads to do it. And there are other problems you can run into if you're not careful with things like deadlock and so on in these scenarios. So in those situations where you have more work that could be usefully done than you have cores to do it and threads to do it on those cores, then you need to come up with a way of being able to expand the number of threads available to the common pool size. And there's ways of expanding it, and then there's also ways that the underlying system will automatically contract when those threads are not being used. So the idea is to expand the number of threads, kind of burst when you have the need for it, and then shrink down later when you don't have a need for it anymore. There are two ways to do this. One way is by modifying a system property. And the system property is rather verbose. It's kind of a mouthful. It's the string java.util.concurrent.forkjoinpool.common.parallelism. And you can set this value before the first use of the fork join pool. So typically when the program starts up. And if you do that, then that value will be the number of threads that are going to be part of the common fork join pool. There are two problems though. Number one, it's hard to estimate the number of threads to set because that's sometimes a dynamic property. And number two, you have to do this kind of in advance before the first use of the fork join pool. The other consequence is that modifying this property has a global effect. So anybody who's trying to use the common fork join pool will now have this many threads, which might be too many, might be too few. It's not a dynamic property. It's set one time when the program starts and then henceforth can't be changed in any meaningful way. And the reason why this is the case is that it has to be done before the fork join pool is initialized. After the fork join pool is initialized the first time using a lazy initialization style approach, kind of a first time in approach, then after that, it can never be changed. So we therefore need some other mechanism, some more dynamic way of being able to change the number of threads that are allocated to the common fork join pool. And we want to be able to do this automatically rather than having to do this in sort of a one-shot, one-size-fits-all model that happens with the system property approach that we just looked at. So the way we do that is by using something called a managed blocker. And managed blockers are super duper cool. We'll talk a lot more about them over the next parts of this lesson. And you'll also get a chance to program with managed blockers for programming assignment 4A. So what the managed blocker does is it makes it possible to temporarily add new worker threads to the common fork join pool on demand. And this is particularly useful when tasks will block on I/O and or if they block on synchronizers like semaphores or reentrant locks or whatever that might cause them to block. Now, a couple things to note. Managed blockers can only be used with the common fork join pool. You can't use managed blocker with a custom fork join pool. You can only use them with a common fork join pool. And another thing to keep in mind is it's often helpful to encapsulate the managed blocker mechanism. So managed blockers are powerful, but they're a little bit ugly to program. And therefore, it's potentially convenient to encapsulate them within another helper class. And we'll talk about that in just a moment when we talk about the blocking task mechanism that we'll look at. So the way this works is when you're going to do an operation that might block or will block, the managed blocker then coordinates with the common fork join pool implementation. And what it does is it arranges to temporarily add a new thread to the common fork join pool while you're blocking. So if you're going to block, then you allow the fork join pool to add another thread to the common fork join pool. If after a while, however, that thread that you were created is not used for a certain period of time, like let's say a minute or so, then it will be terminated, and then the size of the threads in the common fork join pool will essentially contract back to the default number. So it's really only there for temporary. It's kind of like seasonal hiring at Walmart or Amazon. These people, these threads and so on are only there for a short time as long as they're really needed. And after that burst is done, then they can be terminated and they can go away. So that's the end of the overview of the Java fork join framework's common thread pool. And now we're going to talk, of course, in a lot more detail about how this works, and you get a chance to see how to program it and make it work in the programs that you have to write.